Okay, let's dive into the fascinating world of language models and a really stubborn problem that's vexed researchers for, well, for years now. You see, the grand vision of deep learning, what we've all been working towards, it's all about automatically extracting features, building complex understandings, directly from raw data, end to end. No human meddling, just pure AI brilliance. But then you had this really frustrating reality, right? Imagine dedicating your whole career to building these incredibly sophisticated AI brains. I mean, one's capable of learning anything you throw at them. You're thinking about machines that get language like we do, or process complex science better than a supercomputer. And then just when you're about to pop the champagne, you realize, wait a second, we're still manually chopping up text into tokens like it's, I don't know, 1999. It feels like having this amazing supercar, but still needing to hand crank the engine to start it. And honestly, for the longest time, if you tried to skip that manual step or even just messed it up slightly, the whole system would just, well, it would basically crush. The computational costs, all the documented drawbacks, they were just huge barriers.
That really hits the nail on the head. That traditional fixed vocabulary tokenization, often using things like byte pair encoding or BPE, it wasn't just some quirky historical thing. It's a really deeply ingrained, handcrafted step that frankly comes with serious limitations. We're talking about things like poor understanding at the character level, a fundamental lack of sort of real meaning in the tokens themselves that we humans can easily look at and understand. And, a noticeable drop in performance when these models hit complex languages or even totally different kinds of data like code or DNA sequences. It just completely goes against the core idea of deep learning, the philosophy that really emphasizes general methods that learn straight from raw data instead of needing these specialized human-designed bits. It's what Dr. Richard Sutton famously called the bitter lesson back in 2019. The lesson being that powerful general learning methods, if you give them enough data and compute power, they consistently win out over weaker methods that rely too much on human pre-processing or assumptions. And it was definitely a bitter pill for anyone trying to move beyond those fixed tokenizers.
Okay, so our mission for this deep dive then is to really understand how this groundbreaking new approach called HNet finally tackles this fundamental barrier. This isn't just a small step. It seems like it's about making truly end-to-end language models actually work in practice. So let's start by maybe unpacking this tokenization tango a bit more. What does it actually involve, and why has it been such a persistent hassle for these language models? Essentially, this fixed vocabulary tokenization, it's the process of taking raw text like, say, a sentence you type in and chopping it up, compressing it into these predefined smaller chunks.
Right. And these chunks, they might be whole words sometimes, but more often they're sort of subword units, bits and pieces of words. They come from this fixed list that was created beforehand. And while, that approach worked, it was practical for a while, it brings in several pretty significant problems. Problems for you, the listener, and for the models too. First off, there's that limited character level understanding. Because the model only ever sees these predefined chunks, it really struggles with small things like typos or changes in capitalization. It just doesn't see individual characters like you or I would.
Okay, so it's not really reading like we read.
Not at the most fundamental level, no.
Yeah.
And second, there's a real lack of interpretability. These tokens often aren't meaningful units that you or I would recognize. They might be, I don't know, weird parts of words that make sense mathematically to the algorithm, but not to us. And that makes it really hard to figure out what the model is actually processing or why it makes the decisions it does.
That makes sense.
Thirdly, and this is kind of a big one, fixed tokenization leads to poor performance on complex languages or other data types. Think about languages like Chinese, right? No natural spaces between words, or specialized data like computer code or DNA sequences, where our usual idea of words doesn't even apply. These standard tokenizers just aren't built for that. They struggle. And finally, there's fragility. Models can be surprisingly brittle. You miss a space, add an unexpected character, and suddenly the model's performance tanks because its fixed vocabulary doesn't quite match the input anymore.
Wow. Yeah, it really hammers home that bitter lesson idea we talked about, doesn't it? That these general methods learning from raw data should be more powerful than handcuffing them with these specialized steps. So given all these known downsides, why were researchers basically stuck with tokenizers for so long? What did people try before, and why didn't those attempts pan out?
Well, people definitely tried. There were some really smart attempts, but each ran into significant roadblocks. Some researchers explored isotropic architectures, things like Mamba byte or Llama byte. The idea was to process raw bytes directly, character by character. The problem, they were just incredibly expensive computationally, like needed way more processing power. And even then, they still consistently underperformed the models that use tokenization. It's kind of like trying to read a novel one letter at a time while everyone else is reading whole words. Slow and inefficient.
Okay, so that didn't quite work. What else?
Then there were approaches like hierarchical architectures with static chunking. Think hourglass transformer or megabyte. These basically just used fixed size pooling. They'd say, okay, compress every, say, 4 inputs into one chunk.
Yeah.
But the issue there is it's not data dependent. It doesn't adapt, right? Language has variable information densities. Some parts are packed with meaning, others are fluff. Forcing everything into fixed chunks just doesn't capture that well. Performance suffered.
Right, it's too rigid.
Exactly. We also saw hierarchical architectures with external chunking. Models like SpaceByte fell into this category. These relied on sort of outside help. Auxiliary predictor models that would try to find boundaries, maybe looking for white space or sudden shifts in the data's complexity. But that meant they weren't truly end-to-end. They often needed specific tuning for different types of data, like text versus code, making the modalities specific. And often, they still lagged behind in performance. It was like needing a separate little hopper module just to figure out the chunks. And finally, there were some early dynamic chunking attempts. They tried to get the model to learn the boundaries itself, maybe using techniques like umble noise. But they suffered from serious training instability, they were hard to train reliably, and they just couldn't scale up effectively to handle multiple layers of abstraction. So yeah, cracking this nut was proving really, really difficult.
And here's where it gets really interesting, because HNet seems to offer a fundamentally new way through all of that. So HNet's been called this end-to-end dream machine, right? A novel hierarchical network using recursive, data-dependent dynamic chunking. That sounds impressive, but maybe a bit dense. How does it actually pull off this dynamic chunking without someone telling it where the chunks should be? What's the secret sauce?
Okay, let's break it down. At its core, HNet's architecture is kind of inspired by something called a UNet, which you often see in image processing, but they've cleverly adapted it here for sequences like language. Think of it like a funnel and then an inverted funnel. It has 3 main parts. First, you've got the encoder networks, the mathcal. These take the raw, really fine-grained input, like individual characters or bytes, and they compress it, summarize it into richer, more abstract representations, sort of like turning detailed notes into key bullet points.
Okay, compressing the input.
Exactly. Then second, there's the main network, the mathcal. This is where most of the model's brain power lives, where the heavy lifting happens. But crucially, it operates on those compressed chunks from the encoder. This makes it way more efficient, and a really key point. The main network can itself be another HNet. This allows you to stack them, creating multiple stages or hierarchies of abstraction, so you can get bullet points of bullet points, essentially digging deeper into the meaning.
Ah, so it's recursive.
Precisely. And finally, you have the decoder networks, the mathcal-D. Their job is to take the processed information from the main network and decompress it, expand it back out to the original resolution, so the model can still generate fine-grained output, like actual words or characters. Now, the real innovation, the secret sauce as you call it, is the dynamic chunking mechanism, or DC. This is what lets HNet learn how to segment the data without us explicitly telling it where the boundaries are. And what's fascinating here is how the routing module works. It predicts boundaries basically by measuring the cosine similarity between adjacent representations. In simpler terms, it just checks how similar one piece of information is to the very next piece. When there's a significant shift in context, or meaning a semantic shift, that similarity drops, and the model goes, aha, that probably marks the end of one meaningful chunk and the start of another. It's like finding natural paragraph breaks automatically.
That's clever, just based on similarity.
It is, but making that work reliably during training is tricky. That's where the smoothing module comes in, and it's absolutely critical for stability. Imagine trying to learn by only getting yes or no feedback. It's hard to make gradual improvements. The smoothing module basically transforms these hard, discrete chunking decisions into differentiable computations using something called an exponential moving average, or EMA. This allows for what they call adaptive error correction. It lets the model kind of softly adjust its chunking decisions during training rather than making hard breaks.